So we know that trigonometry is the study of triangles, and when we're looking at these primary trigonometric ratios, we're going to be specifically looking at right angle triangles, right? So these guys are only used for right angle triangles, and these ratios can help us to look at the relationship between an angle, a reference angle, and its particular side length in a triangle, right? Now, we can understand that angles, when you use theta to represent angles in a triangle, or basically angles in any kind of geometric shape, theta is going to be representing angles, and we know that this total sum of angles in a triangle should be 180 degrees. Okay? So keep this in mind, right? And the primary trigonometric ratios that we're going to be looking at include the sine, cosine, and tangent ratios. Okay, so these are some of the values of the ratio. These are like formulas that you want to kind of memorize. Sine of an angle is basically equal to the opposite side over the adjacent side. Sorry, opposite side over the hypotenuse. Cosine of an angle is equal to the adjacent side over the hypotenuse. And tan of an angle is equal to the opposite side over the adjacent side. And notably, you can memorize these using the mnemonic SOHCAHTOA. Okay, so using this mnemonic, you can see that S here represents sine, C represents cosine, and T here represents tangent. Okay, so sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tan is opposite over adjacent. Now let's take a look at what do these side lengths mean, right? So if we have a triangle here, say this is our triangle. Right, it has to be a right angle triangle. You can only use these primary trig ratios for right angle triangles. And let's say that we label this triangle A, B, and C. Okay? You can note here that this right angle here represents that it is a right angle triangle. The side length opposite of the right angle is always the hypotenuse. Okay, so I'm going to explain what the hypotenuse is, but the hypotenuse, I'm just going to use HYP to abbreviate that, but the hypotenuse is the longest side in a right angle triangle. Okay, so it's the longest side in a right angle triangle, and basically we can also label, instead of writing this as hypotenuse, we can also label this based on the angles of our triangle, right? So we can understand that I've labeled this triangle ABC. Each of these capital letters represent a vertex, and basically they also represent the angle. So this is angle A, this is angle B, this is angle C, and this is angle B, right? Opposite of each angle is a respective side length. So this is side length A, this is side length C, and this is side length B. And we represent side lengths using lowercase letters. We use angles and vertexes or vertices in capital letters. Okay. Now, so we said the hypotenuse is always going to be right across the right angle, but let's say we wanted to look at the opposite or the adjacent side. Well, to look at the opposite or the adjacent side, we need a reference angle, right? So we can use angle A or we can use angle C. We tend to use acute angles for reference angles, right? So we can't really use this right angle. So having said this, let's say that instead of labeling these angle A and angle C, I label this a different way, right? Let's call this guy angle alpha, and let's call this guy, let's call this guy angle beta. Okay, so this is beta, this is alpha, right? And we can understand that if I'm taking a look at, we can understand that angle alpha and angle beta should be equal to 90 degrees. Okay, that these are two complementary angles, right? Complementary angles are angles that add up to 90 degrees, because we know that the total sum of angles in this triangle should equal 180, and this is already 90, right? So these are complementary angles, complementary well, they should be spelled with an E, complementary angles. And let's take a look at the ratio, right? So we can find that if we use angle alpha as a reference angle, then this side length A is our opposite side. Okay, so this is my reference angle. A is my opposite side. This side length B here will always be hypotenuse, so as a result, this is my adjacent side. Okay, let's take a look at angle beta. So if I'm looking at angle beta, you can notice that, whoops, if I'm looking at angle beta, you can notice that now this side becomes the opposite side. This hypotenuse will still stay the same, and then as a result, this becomes the adjacent side. So depending on our reference angle, it changes the ratio. So let's take a look at our primary trig ratios for alpha. Say we looked at sine alpha. Sine alpha is basically equal to the opposite side, A, over the adjacent side, over the hypotenuse, I did that twice, over the hypotenuse, B, right? So this is going to be equal to A over B, it's opposite over hypotenuse. Now if we take a look at cosine alpha, right, then we're going to have the adjacent side, C, over the hypotenuse, B. And if we take a look at tan alpha, we'll have the opposite side over the adjacent side, so it's going to be A over C. Okay? Now let's take a look at if beta was a reference angle. Okay, so let's say that sine beta here is now, the opposite side is now going to be C. It's going to be C over hypotenuse, which is B. Cosine of beta is equal to the adjacent side, right? So if we look at beta, the adjacent side now becomes A. We're going to get A over the hypotenuse, B. And tan beta is going to give us opposite, which is now C, over the adjacent side, which is basically A. Sorry, over A, right? So now we get C over A. And you can actually notice a few things here. You can notice here that sine alpha is basically equal to the ratio of cos beta. And we can also notice that sine beta is equal to the ratio of cosine alpha. Okay, so there should be some kind of link here, right? And we want to kind of explore this, right? So if we do explore this, we can understand that we know that alpha plus beta is 90 degrees. We can understand that beta can thereby be written as 100 is 90 degrees minus 90 degrees minus alpha. Okay, so having said that, this becomes true that sine 90 degrees minus alpha is equal to cosine alpha. Okay, and it's true the other way around as well, right? That alpha is 90 degrees minus beta, right? So in that sense, we can understand that cosine 90 degrees minus beta is equal to sine beta. Okay, and this is going to be true for whatever angle you look at, right? So this actually brings up a really important identity that we're going to be exploring later, which is basically called the co-function identity, right? You can write one trig ratio in terms of another, right? So this is really useful to take a look at this triangle, and basically you can understand here that sine theta is basically cosine 90 degrees minus theta, right? So this is your co-function identity, and we're going to take a look at this later on. But basically you can convert one angle into its equivalent cosine angle, right? You can convert the sine ratio into its equivalent cosine ratio, and you can look at the value of the angle that will keep the ratios constant. Okay, so we'll kind of explore this further on. Alright, for the following triangle, determine the indicated values, right? So we know this is a right angle triangle, so we can use our primary trig ratios. If we want to solve for x here, what we can do here is we have a reference angle, it's 42 degrees. We have the hypotenuse, which is 5 centimeters, and this is where the primary trig ratios become really useful, is that we can understand that if you wanted to solve for x, using the reference angle 42 degrees, this is going to be our opposite side. This is going to be our hypotenuse, and this will always be our hypotenuse. This won't change, right? Because we can basically, because there's a right angle present, right? So the side length that's always across the right angle is always along the side. And we can solve for x by using the sine ratio because we have the opposite side and we have the hypotenuse. So you have 3 bits of information. If you know 2 out of the 3, you can solve for the missing link, right? I'm going to do sine 42 degrees is equal to the opposite side, x, over the hypotenuse, which is 5. In this case, x is equal to 5 times sine 42 degrees. And in this case, x is equal to 5 times sine 42 if we punch this out. And you can notice that you can actually find the value of the ratio if you plug it into your calculator. So make sure the settings of your calculator is in degrees, right? We'll take a look at other measurements of angles later on, right? So as long as your angle is in degrees, you can kind of solve for this, right? So in this case, sine 42 is equal to 0.6691. Okay, so I'm just going to use 4 decimal places for the time being. So it's 0.6691. If I multiply this by 5, we basically get 3.3457, and if I round this off, let's round it to 2 decimal places, it's 3.35 centimeters. Okay, so we actually solved for x, right? So it's 3.35 centimeters, right? Before solving for y, we can actually note that beta here, 42 degrees plus beta, should equal 90 degrees because these two are examples of complementary angles, right? So you could have actually started by doing that first. So beta here is 90 degrees minus 42 degrees, which is basically, should be 48 degrees, right? So this is 48 degrees, okay? And put the degree sign and note that it is in degrees. It's important to keep the units on. And then what you can do here is you can solve for y really 3 different ways, right? You can use reference angle beta, you can use reference angle 42 degrees, or you can use Pythagorean theorem. And we can actually note that you will get the same value. So I'm going to just show you guys that. But remember that right angle triangles allow us to use Pythagorean theorem. So we can understand that x squared plus y squared is equal to 5 squared, right? Because a squared plus b squared should be equal to c squared according to Pythagorean theorem. And in this case, we already solved for x. So 3.35 squared plus y squared, which we were trying to solve here, is equal to 5 squared. So y squared is equal to 5 squared minus 3.35 squared. And if I calculate this, right, I get 25 minus 3.35 squared. So that's going to give us 13.778. Okay, and y here, if I square root it, right, because you want to solve for y, not y squared, you get square root of 13.778. And in this case, what you're going to get here, 3.71 approximately. Okay, so I'm just going to keep all answers in 2 decimal places. So this is 3.71 centimeters, right? I'm going to show you that you're going to get the same answer by evaluating it using the trig ratios. Let's tell me to use beta just to kind of show you that you can do this multiple different ways, right? And so one of the beauties of math is that you don't have to do it a set way. You can approach problems in multiple different ways. Now, if I use beta here, and we know beta is 48 degrees, I'm going to be using, because this becomes my reference angle, y becomes the opposite side, right? So I'm just going to use sine 48 degrees, right, which is beta, is equal to the opposite side, y, over the hypotenuse 5. Y is equal to 5 times sine 48 degrees, and y here is equal to 5 times sine 48, which is also 3.7157 centimeters. So that's approximately 3.72 centimeters. which is basically what we have here, right? So it's like 3.715. I could have had a rounding error here that's like caused a slight deviation, but you can notice here that it's the same value, right? So this just indicates that there's multiple different ways you can do this. We can also use the 42 degrees to solve for y by using cosine. Let's see that. I'm going to show you that it gives you the same value. Like if I do cosine 42 degrees, then it's adjacent side, so this becomes the adjacent side, right? Is adjacent side y over the hypotenuse 5, then y becomes, if I multiply 5 to both sides, you can solve for y, so 5 times cosine 42 degrees, and y is equal to 5 times cosine 42, which is approximately 3.7157 as well, right? So ideally, we would probably want to round this to 3.72 centimeters, but at the end of the day, it's the same thing, right? So this can show you guys that you can do, you can approach trig questions when you're solving for a missing side multiple different ways, and if the case does present itself, you can also employ Pythagorean theorem. So all of these things are related. So that's what the power of trig really. All right, let's solve for the following triangle by finding all missing sides and angles. Now, in this case, we're not given any angles. We know this is a right angle triangle, so we can utilize our primary trig ratios, but we are given two sides, right? Now, you can actually solve for side length x by using Pythagorean theorem, right? So I'm going to just do that out really quickly, but I also want to demonstrate that you can do this by using trig. Now, if we do use Pythagorean theorem, we can understand that c squared, which is the hypotenuse, and the hypotenuse is always located across from this angle, from the right angle. C squared, the hypotenuse, minus b squared, which is any of the other two sides, is equal to a squared, right? So in this case, a squared is x, right? So we can understand that 7.2 squared minus 4.1 squared is equal to x squared. So therefore, x is equal to the square root of 7.2 squared minus 4.1 squared. Okay, so in this case, we can see that if I crunch this out in my calculator, it's 7.2 squared minus 4.1 squared, and this is going to give us 5.9186 centimeters. Okay, I'm going to keep it into 4 decimal places because I want to see how accurate my trigonometric procedure in calculating this missing side will be to this Pythagorean theorem. Okay, so we calculated that x is 5.9186 centimeters. Now, the big question here is how do we find these angles, right? Now, to find the angles, I'm going to use, for alpha, let's use rad here. Okay, so this is angle alpha. To find alpha here, right, we can notice that this becomes the opposite side. So x is the opposite side, right? Let's say we label this side length A. Let's call this guy C, and let's call this guy B, right? So this is side length C, this is side length B, and this is side length A, right? And it's just another way of looking at it. And so this is your opposite side here, and this will always, C will always be a hypotenuse, so this is going to become the adjacent side. B is our adjacent side, right? And we can understand here that if we didn't solve for x, we do have the value of our adjacent side over hypotenuse. So cosine of alpha is equal to 4.1 over 7.2. Okay, let's assume that I didn't solve for x here. Okay, I'm going to just look at the information that I've given, and if you figure out what this value of this ratio is, 4.1 divided by 7.2 is going to give us 0.5694. Okay, so we get 0.5694. Now, in order to solve for alpha, I need to get rid of this cosine, and we do something called an inverse. It's called the cosine inverse. We do the cosine inverse of cosine alpha, and this actually cancels out the cosine. So each function has its own inverse, right? So if you have sine theta, right? If you do the sine inverse of sine theta, then you basically get theta. If you do cosine inverse of cosine theta, you basically get theta because the cosine and the cosine inverse cancel out. And if you do the tan inverse of tan theta, you basically also get theta. So the inverses just cancel out the ratio, like the value of the ratio. And in this case, we can see here that cosine inverse of cosine alpha, it will give us alpha. But whatever you do to one side of the equation, in order to keep it the same, you have to do it to the other side. So cosine inverse of 0.5694. So now you can see that alpha is equal to the cosine inverse of 0.5694. And if I punch this in my calculator, you should see that alpha is equal to 55.29 degrees. I'm going to round to the nearest degree. So let's do 55 degrees. So if alpha is 55 degrees, you can then solve for beta, because we can understand that beta is complementary to alpha, right? Alpha and beta are complementary angles. And in this case, beta should be equal to 90 degrees minus alpha, which is 55 degrees, which should also be 90 minus 55 is 35 degrees. Now let's say that we want to solve it a different way. Well, using beta here as my reference angle, then this becomes the opposite side, right? This will become the adjacent side, and then the hypotenuse will still remain at 7.2. So in that sense, we can understand the sine of beta using our previous values will give us 4.1 over 7.2, right? We found the ratio of this, so sine of beta is equal to 0.5694, right? We calculated the ratio of this. So beta here, if you want to solve for beta, what you need to do here is you need to do the sine inverse of both sides. So sine inverse of sine beta is equal to the sine inverse of 0.5694, and then the sine inverse and the sine cancel out, so we get beta is equal to the sine inverse of 0.5694. So if I do that in my calculator, you actually get a different value. You actually get the same value. You get like 34.708 degrees. If I round that to the nearest degree, it's about 35 degrees. So you can actually see that you get the same value. Okay, this is really useful, and it does really help us to kind of understand this, right? So you can actually see that beta will give us the same value. Now, in that sense, right, so we know how to solve for alpha and beta, right? So alpha here is 55 degrees, so rounding into the nearest angle, and beta here is, let's say, beta here is 35 degrees if I round to the nearest angle. And I want to solve for x. Well, you can use either any of these two angles now, right? Let's just use alpha, and you'll see that you'll get the same answer. So let's say we're using alpha. So alpha, this will become the opposite side, so we can understand the sine of alpha, which is basically 55 degrees, is equal to basically x, the opposite side, over the hypotenuse, 7.2. If I want to solve for x, I'm going to multiply 7.2 to both sides, cancels out. X is equal to 7.2, times sine 55 degrees. And in this case, x is going to be equal to, so 7.2 times sine 55 degrees is going to be equal to about 5.8978, right? You can notice that it's very close. Like this is going to be 5.9, this is going to be 5.9, right? And one of the reasons because is I rounded the angle off, right? So if you do keep it as accurate as possible, right? I had 55.29, right? So if I did 77.2 times sine 55.29, you can see that you'll get 5.9187. So it's very close. It's exactly the same, right? Like if I do sine 55.29 in my calculator, you can actually note that you would get 5.9187. Right, so if you actually use the original value, you can see that the margin of error between Pythagorean theorem and utilizing trig here, right, the trig value and using Pythagorean theorem, using the trig ratios in Pythagorean theorem, these are very close, right? So now we've solved for x, and we can say that x is equal to, let's say, 5.92, right? And that's basically our triangle in a nutshell. We've solved for a triangle. So you can use a combination of these trig ratios, the inverse of the ratios, Pythagorean theorem to basically solve out a right angle triangle. So it's really useful to understand. So previously we took a look at our primary trig ratios, which include the sine ratio, sine theta, which is equal to the opposite side over the hypotenuse. We also looked at the cosine ratio, which was equal to the adjacent side over the hypotenuse, and we also looked at the tan ratio, which was equal to the opposite side over the adjacent side. And we noted that these primary trig ratios were only used for right angle triangles. As long as there was a right angle triangle, we could use these ratios, right? Now these guys also have an associated reciprocal ratio. Now reciprocal basically means that we're dividing anything by 1, and when we take a fraction, if we have like a over b, right, the reciprocal, which is 1 over a over b, if we do the reciprocal of this, we'll actually get b over a, right? And any fraction multiplied by its reciprocal will give us 1, right? That's really the purpose of a reciprocal, right? It just basically a fraction, a reciprocal fraction times its original fraction will give us 1, right? Because you can see here that's AB over AB, right? Anyways, so these guys actually have reciprocal ratios, and the reciprocal ratio of sine theta, 1 over sine theta, is equal to something called cosecant theta. Okay, so cosecant is the reciprocal of the sine ratio. The reciprocal of cosine is something called secant, right? Right, and secant is 1 over cosine theta. Yes, it's called secant. And the reciprocal of tan is something called cotangent. Cotangent is 1 over tan theta, right? So having said this, using this definition, right, cosecant theta is basically the hypotenuse over the opposite side. Secant theta is the hypotenuse over the adjacent side, and cotangent is the adjacent side over the opposite side. Okay, so let's keep this in mind for further discussion. Alright, so let's take a look at special angles. So special angles are angles that we will actually know the exact value of their ratios for a respective function, like a sine, cosine, tan, or its reciprocal functions, right? And these angles include 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Okay. Now for the first set of angles, the 30 degrees, 45 degrees, and 60 degrees, we can determine the exact value of their respective ratios for each of the 3 primary trig functions, right? We can find the exact value of these ratios by using something called a special triangle. Okay, so we're going to be using a special triangle for these 3 values to demonstrate that. And then for these other values left over, the 0 degrees, the 90 degrees, the 180, the 270, and the 360, we're going to be using something called a unit circle. So I'm going to start with the demonstration of these special triangles, and then we'll take a look at the unit circle, right? Okay, so I'm going to start the special triangle depiction of these special angles. We're going to find the values, exact values of their ratios for 30, 45, and 60 for the sine, cosine, and tan functions. Okay, so let's start with our first special triangle. I'm going to call this special triangle number 1. It's not its particular name, but I like to kind of differentiate between the two. And you guys have to just memorize this. I had to construct it, but this is technically an isosceles triangle. Okay, so let's say that this is your isosceles triangle here, and then this is, and these have to be right angle triangles because these are primary trig ratios. Okay, this is side length of 1, side length of 1, and then this is square root 2. Okay, so I'm just going to clean that up a little bit. Sorry about that, guys. Okay, so this is your right angle triangle. These are the side lengths of 1, right? You can notice that these are the same. And the angles associated are 45 degrees and 45 degrees. We know an isosceles triangle will have 2 it's the same size, and as a result, two same angles, right? And we can notice that we can actually find the exact value of one of these angles, because the other angle is the same thing. It has to be an acute angle. You notice that sine 45 degrees is basically equal to, and this becomes a reference angle, so let's just do it here. So this is the opposite side. The hypotenuse is always across from the right angle, so this is the hypotenuse, and this is the adjacent side. So you can actually see here that sine 45 is 1 over square root 2, right? Now this ratio has a radical on the denominator, and we prefer not to have a radical, so I'm just going to multiply by square root 2 to both the numerator and denominator, so you actually get square root 2 over 2. So sine 45 is equal to square root 2 over 2. I'm going to be using this ratio value more consistently because of the fact that it's in better form. And if we take a look at cosine 45 degrees, well, we'll actually see that it's the adjacent side over the hypotenuse, and you'll actually get the same ratio, 1 over square root 2, which is square root 2 over 2, right? And this actually kind of coincides with what we showed earlier, that sine theta is equal to cosine 90 degrees minus theta, right? So you can notice here that sine 45 degrees is equal to cosine 90 minus 45, which is equal to cosine 45. So they actually have the same ratio. So that's one way we can actually see that, right? So you actually get square root 2 over 2. And tan 45 degrees is basically equal to opposite over adjacent, which is 1. So therefore, the values for the special triangle number 1 here, right, we can notice that sine 45 degrees is square root 2 over 2. Cosine 45 degrees is square root 2 over 2. And tan 45 degrees is 1. Okay, so those are the summary of our values for 45 degrees. I'm just going to make a box here. So make sure you guys memorize this, but really the idea is just memorize the special triangle here, right? So if you memorize the special triangle, you can actually come up with these values, right? Now the next special triangle that I'm going to be looking at here is basically going to help us to find 30 degrees and 60 degrees, right? So I'm just going to clear some room here, so I'm just going to erase this out. Okay, so now we're going to look at the other ratios, the exact value of the ratio for the other angles, 30 degrees and 60 degrees, by using these sine, cosine, and tan functions. Okay, so this time our triangle is going to look something like this. Whoops. Okay, so the triangle is going to look like this. It's going to have a side length of 1, 2, and square root 3. Okay, this angle here is 60 degrees, and this angle here is 30 degrees. Now, a quick way of kind of remembering how to create this special triangle is what we could do here is we take an equilateral triangle. Okay, let's say that this is our equilateral triangle. We take our equilateral triangle, right? I didn't draw the scale, but kind of just bear with me here. Let's say that this is 2 units by 2 units by 2 units, and then this is 60 degrees by 60 degrees by 60 degrees. What we do is we basically take our magical scissors here and we cut this guy in half. Okay, so we cut this guy in half, right? And when we cut this guy in half, we actually create a right bisector. Okay, so when you create a right bisector, what happens here is you create a 90-degree angle, and when you cut this in half, look what happens, right? So you basically end up with this. You can see that the 2 unit is retained. This guy becomes 1 unit, and half of the 60 degrees is going to give you 30 degrees, and you also create this 90-degree angle. So this is a right angle triangle, and that's how you get this triangle. So that's a good way to memorize it if you guys, need some kind of backstory to help you with that. And then we can figure out some of our ratios. So let's start with our reference angle of 30 degrees. Okay, so I'm going to start with 30 degrees here. Okay, and in this case, now this becomes the opposite side, right, across from the right angle will always be your hypotenuse, and then this guy, as a result, will become the adjacent side. Okay, so now we can see here that sine 30 degrees is equal to opposite over hypotenuse 1/2. Cosine 30 degrees is equal to adjacent over hypotenuse, which is square root 3/2. And tan 30 degrees is equal to opposite over adjacent, which is basically 1 over square root 3, or you can write this, if you multiply by square root 3, as square root 3/3. This is more preferable, right? So we have our values of 30 degrees for each of these trig functions. Now let's take a look at the 60-degree version, right? So if we take a look at the 60-degree version, I'm going to just get rid of this, just get rid of the coloration here. Whoops, got rid of our entire triangle by doing that. Okay, so let's say this is our triangle, right? And basically we can note here that the hypotenuse would be conserved, right? Still 2 here. And this time we'd be looking at 60 degrees. Okay, so let's take a look at this angle now. Okay, so if I'm looking at this angle, right, this is the opposite side. So I'm just going to erase this. So now this guy becomes the opposite side. The hypotenuse is still conserved, and this is your adjacent side, right? So now you can see here that sine 60 degrees is equal to opposite over hypotenuse, square root 3/2. Cosine 60 degrees is basically adjacent over hypotenuse, which is 1/2, and tan 60 degrees is equal to square root 3/1. You can also see that this cofunction identity is still conserved, right? Now we can see that sine theta is equal to cosine 90 minus theta, and cosine theta is equal to sine 90 minus theta. And you can notice this by just kind of comparing these two, right? Like if I compare sine 30 with cosine 60, they'll have the exact same value, right? But also if I compare this cosine 30, if I compare cosine 30 with sine 60, you'll see that it has the same value as well, right? So this will kind of work for all scenarios, right? And these are our values of our special triangle. To summarize the exact values of our ratios regarding the functions of our primary trig functions of our special angles, right? We looked at 2 special triangles here, right? And this was special triangle 1, and then this was special triangle 2, right? And this kind of helped us to determine the special angles 30 degrees, 45 degrees, and 60 degrees. If I make a summary chart regarding this, okay, so I'm just gonna construct this. Okay, where we have theta on top here, this is 30 degrees, 45 degrees, and 60 degrees, right? Let's say that we have, this is sine theta, right, our sine function, cosine theta, cosine function, and tan theta, right? We showed that sine 30 here was the value of 1/2. Sine 45 was square root 2/2, and sine 60 is square root 3/2. Okay, cosine 30 here is square root 3/2, and it's equal to sine 60, right? Remember that we looked at the cofunction identity. Cosine 45 was the same as sine 45. Once again, you can determine that using the cofunction identity, square root 2/2. Cosine 60 is 1/2, which is the same as sine 30, right? And then tan 30 here was square root 3/3. Tan 45 was 1, and tan 60 was square root 3/1. So these are some of the values that you want to look at. And you have to kind of memorize these values because they're going to become really important as we kind of progress through this, right? Let's say I gave you a question where we had evaluate, and this is where you wouldn't be using a calculator. Evaluate for each expression, and let's say we had sine 45 degrees times cosine 30 degrees minus, let's do tan 30 degrees. Okay, so let's say we had something like this. In this case, sine 45 was square root, let's use a different color, square root 2 over 2. Cosine 30 here is basically square root 3 over 2, and tan 30 is basically square root 3 over 3. In this case, if we multiply these two, right, so we get 2 times 2, which is 4, square root 2 times square root 3 is square root 6 minus square root 3 over 3. And then what we want to do is, in order to combine the numerators, I'm going to find a lowest common denominator, make the denominator the same. So I'm going to use 12 here. So in that case, I'm going to multiply this guy by 3 and this guy by 4. So you get 3 square root 6 minus 4 square root 3 over 12. And that's really as far as you can go. You can't really simplify this any further. So this is basically your answer. Okay, so that's really the idea. You have to be able to fully simplify. You have to be able to fully memorize all these values, and it's going to become really useful later on as we look at just evaluating expressions, but specifically it's going to be really useful in our discussion of related angles, where we're going to be looking at a related acute angle to find values of obtuse angles. So guys, really just memorize these values. It's going to be really important. We'll also be looking at the other special angles, which include 0 degrees, 90 degrees, 180, 270, 360. And I'll show you guys how to calculate for that, but we're going to be introducing the unit circle. Alright, to summarize everything we've kind of discussed, we looked at some of the functions, the trig functions, the sine function, the cosine function, the tangent function. We also looked at their trigonometric functions, which include the cosecant function, the secant function, and the cotangent function. And we also we looked at those ratios, and we also discussed this notion of special angles, which included the 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180, 270, and 360 degrees. And we discussed how these special angles, the exact values of the ratios, could be determined by using the special triangles, the unit circle. I'm just going to summarize all of this out for you guys. Right, so let's start with, these are just values of theta here. Right, so this is theta. And let's start with sine theta, cosine theta, tan theta. And then we'll also look at the reciprocal values, right? I would just recommend memorizing sine, cosine, tan, but I'm just going to put all of this out there for you guys, just in case you wanted to memorize the rest. I don't think it's useful, but it's better to memorize sine, cosine, tan, your primary trig ratios, and then for your reciprocal, you just have to take the reciprocal of their ratio values. You just flip the numerator and denominator. But I'm just going to put all of this out there for you because it does bring up a very important point that we will later on discuss when we study these, the behavior of their trig functions, of these trig functions graphically, right? So we looked at sine, cosine, tan. We'll also look at cosecant theta, which is the reciprocal of sine, right? Cosecant theta is 1 over sine theta, right? Secant theta is 1 over cosine theta, and we'll also look at cotangent theta, which is 1 over tan theta. Okay, so keep this in mind, guys. So I'm going to write secant theta here and cotangent theta here. Okay, I'm going to start with cosine and sine really quickly first. So for the unit circle, we had sine theta, sine of 0 is basically 0, cosine of 0 is 1. We also looked at, I think I briefly discussed the quotient identity, that tan theta, and I showed you guys this through the proof of the unit circle, that tan theta is equal to sine theta over cosine theta. So having said this, although we had values from the special triangles, which included 30 degrees, 45 degrees, and 60 degrees, where we actually determined tan theta, For the unit circle, you can actually just divide sine over cosine to find tan. So when you do tan of 0, for instance, right? So tan 0, let's just do it here. So tan 0 here is equal to sine 0 divided by cosine 0. Okay, so tan 0 is sine 0 divided by cosine 0. In that case, sine 0 here is 0, cosine 0 is 1, so tan 0 is 0 degrees. And that's how you would basically solve for it. Sine 30 degrees, we said was 1/2. Cosine 30 was square root 3 over 2, right? And as a result, tan 30, you could divide these two, right? And you can prove that here if you wanted to. So tan 30 degrees should be equal to sine 30 divided by cosine 30, which is basically equal to 1/2 divided by square root 3 over 2. If I simplify that, 1/2 times 2 over square root 3, so you actually get 1 over square root 3, which we simplified as square root 3 over 3. Right? And we know this is true because by drawing the special triangle, this was square root 3 over 3. Okay? Sine 45 was square root 2 over 2. Sine 60 was square root 3 over 2, which is the same value as cosine 30. And we looked at that notion that sine theta is equal to cosine 90 degrees minus theta, right? And vice versa, that cosine theta is equal to sine 90 degrees minus theta as well. Okay, so this is another thing that we investigated. So cosine 45, same value as sine 45 square root 2 over 2. Cosine 60 is the same value as sine 30, which is 1/2. Sine 90 was 1. Cosine 90 was 0, right? And tan 90 as a result is 1 divided by 0, which doesn't exist. Okay, so 1 divided by, and whenever you have 0 on the denominator, it doesn't exist. Tan 45 was 1. Tan 60 was square root 3 over 1, right? Sine 180 from the unit circle we determined was 0. Cosine 180 we determined was -1, and then 0 divided by -1 is 0. Right, sine 270 was -1. Cosine 270 was 0. Tan 270 is sine 270 -1 divided by cosine 270, which is 0. Doesn't exist. Right? Sine 360 was 0, cosine 360 is 1, and tan 360 is 0. Okay? So those are the values for our primary trig functions, right? These are your primary trig ratios. Let's take a look at the reciprocal values, right? Cosecant 0 degrees is basically the reciprocal of sine. Now this is basically, for sine theta, this was 0 over 1, right? So it was basically 0. So cosecant is 1 over 0, which is undefined, right? Because this is 0 over 1. If you do the reciprocal, it should be 1 over 0. So this is undefined, does not exist, right? Secant, however, it's the reciprocal of cosine, right? So pretend that this is 1 over 1, so secant, you just flip it, so you'll get the same value, it's 1. Okay, guys? Right? Cotangent doesn't exist, right? So cotangent theta is basically, if tan theta is sine over cosine theta, then cotangent is cosine theta over sine theta, and sine theta doesn't exist, right? Well, sine theta is 0, right? So it's 0, 1, it also doesn't exist. Okay, so keep that in mind. Cosecant 30 is basically the reciprocal of sine 30, so it should be 2 over 1, right? Secant 30 is 2 over square root 3, and you guys can simplify this, right? You can write this, if you multiply by square root 3, right, you get square root 3 over 3. Okay, so I'm sure you guys know how to do the radical simplification, right? So it's 2 square root 3 over 3. And then cotangent theta is the reciprocal of sine, so you get 3 over square root 3. And if you multiply this guy out, right, you get 3 square root 3 over 3, which is basically square root 3. Okay, so square root 3. Cosecant 45 here is the reciprocal of sine, so it's going to be 2 over square root 2, which is square root 2 over 1. Okay, and same idea with secant. And then cotangent here is still 1. Okay. For cosecant 60 degrees, that's going to be the reciprocal of sine. So it's going to be 2 over square root 3, which we stated was 2 square root 3 over 3. Okay. The reciprocal of cosine 60 is 2 over 1. And then this guy here is going to be 1 over square root 3, which is basically square root 3 over 3. Okay, guys? Okay, so then we also have cosecant 90, which is 1, it's reciprocal. Secant 90, on the other hand, we know that cosine 90 is 0, so it's 1 over 0, so it doesn't exist. Okay, and cotangent also doesn't exist, right? Because you can see that it's sine is cosine 90. Oh, sorry guys, wait. So cotangent 90 is equal to cosine 90 over sine 90, right? And that's going to give us 0 over 1. So this actually does exist. So cotangent would actually be 0 here, right? So there the restriction is gone now, right? So keep that in mind, right? So in this case, cosine 90 is 0, cosine 90 is 1, so that's why it will exist. And then we can figure out the rest. So cosecant doesn't exist because it's 1 over 0. Secant here will be -1, and then cotangent would be, let's do it out here. So cotangent cotangent 90, sorry, cotangent 180, just erase this out. Cotangent 180 is equal to cosine 180 over sine 180, and once again this is undefined as well, right? So this doesn't exist either. Okay, cosecant 270 is still -1. Secant 270 doesn't exist because you get 1 over 0. Cotangent 270, let's write that out. 270 is basically equal to cosine 270 over sine 270, when this is going to give us 0. Okay? We're 360 here. This doesn't exist because you get 1 over 0. This is 0 over 1. You flip it. Secant, you get 1. Right? And then cotangent 360 is going to be the same as 0 degrees. It also doesn't exist. Good? And this is your full out chart, guys. Okay, so it did take us a while, but for the most part, I would recommend kind of knowing these out. Once you know these out and you know the quotient rule, you can actually figure out the rest. And you know that reciprocals, you just flip the numerator and denominator, right? So, but I decided to do the full chart for you guys so you guys can have a good summary of all of this. Alright, so that's the idea of special angles. So I would really recommend you to memorize this set that I've highlighted in yellow. Alright, let's evaluate the following expression and reduce all fractions where possible. So we're going to be using some of the special angles that we looked at, some of the values that we looked at. Sine 60 is going to have a value of square root 3 over 2. So guys, you want to try and memorize that table that I constructed earlier. Tan 30 here is square root 3 over 3 minus cosine 45 is square root 2 over 2, and times sine 30 is 1/2. Okay, so what I'm going to do here is I'm going to simplify this. Now you're dividing these two fractions together, so you get square root 3 over 2. And when you're dividing two fractions, you multiply by the reciprocal, 3 over square root 3. And you notice that square root 3 divided by square root 3 cancels out, and you actually get 3 over 2. Okay, so instead of writing all of this out, you can write that as 3 over 2, right? If I multiply these two together, you should get square root 2 over 4. So in my next line, I'm going to write 3 over 2 minus square root 2 over 4. And now what you want to do here is you want to find the lowest common denominator. So the lowest common denominator here is 4. So what I'm going to do here is I'm going to multiply this by 2 and this by 2. So you get 6 over 4. And then you basically can get 6 over 4 minus square root 2 over 4. And you could just leave your answer like this, right? We're trying to make sure that we have proper form where we simplify our fractions as much as possible and that the denominator doesn't have a radical. So this is our final answer, to that question. So this was pretty straightforward. You just gotta have to memorize some of the trig ratios, all right? All right, let's take a look at a much more challenging example. Here we want to evaluate the following expression, reduce all fractions where possible. We want to make sure that there's no radicals on the denominator. Okay, so this time I've thrown in some reciprocal ratios. Now we need to kind of note here that cosecant 60 degrees is basically 1 over sine 60, and sine 60 is basically square root 3 over 2, so 1 over this is basically 2 over square root 3. Now I'll simplify the radical afterwards, right? But if you did want to simplify the radical, you can multiply by square root 3, so you get 2 square root 3 over 3. Okay, so that's the cosecant 60. Cosine 45 degrees, we know the value is square root 2 over 2. And cotangent 30 degrees, this is a reciprocal, is equal to 1 over tan 30 degrees, which is basically 1 over square root 3 over 3, right? And 1 over square root 3 over 3 is 3 over square root 3. And we can simplify the radical by multiplying by square root 3. So we get 3 over square root 3 over 3. So 3 times square root 3 over 3. So that's that for the first rational on the left. Now let's take a look at the second rational expression on the right. We have secant 45 degrees, which is 1 over cosine 45 degrees, which is basically 1 over square root 2 over 2, which is 2 over square root 2. Okay, so this is secant 45 degrees, it's 2 over square root 2, right? And we can multiply this by square root 2 to simplify it, so we get 2 square root 2 over 2. Okay, then we can take a look at sine 60. We know the value of this is square root 3 over 2. And we have cosecant 30 degrees, which is 1 over sine 30 degrees, which is 1 over 1/2, which is basically 2 over 1. Okay, now what I'm going to do here is I'm going to take all of these simplified values that I looked at and I'm going to put it back into my expression. So cosecant 60 we calculated was 2 times square root 3 over 3. Cosine 45 was square root 2 over 2. Cotangent 30 was 3 square root 3 over 3, right? And we're going to add this with secant 45, which we calculated was 2 square root 2 over 2, sine 60, which was square root 3 over 2, and cosecant 30, which is basically 2 over 1, right? And then if I simplify this, I'm going to multiply this out, right? So you get 2 square root 3 times square root 2 here is 2 square root 6 over 6. Okay, I'm going to divide this by 3 square root 3 over 3 plus, right, square root 2 times square root 3, so 2 square root 6 over 4 over 2. Okay, let's simplify this. Let's do this using a different color here. If I simplify this, I'm going to take a look at these two. 2 square root 6 over 6 times, because I'm dividing these two, I'm multiplying the reciprocal, 3 over 3 square root 3, right? And you can notice here that you get 6, 2 times 3 is 6, divided by 6 is 1. So you basically get square root 6 over 3 square root 3. And what we could do here is multiply by square root 3 to simplify this. And we get square root 18 over 9. Okay, so we get square root 18 over 9. I'm going to keep it like that for the time being. We can simplify that afterwards. So that's basically all of this guy here. So this is square root 18 over 9. And then let's take a look at this notion here. So let's take a look at the fraction on the right. And in this case, we get, I use a different color here. I use green. In this notion, we get 2 square root 6 over 4. For dividing by 2, we're multiplying by 1/2. We basically cancel this out. We get square root 6 over 4. Okay. So now in my next line, this is what I'm left with. Square root 18 you can actually write using radical expressions as 9 times 2, which is square root 9 times square root 2, which is 3 square root 2. So you're going to have to memorize you have to kind of know your radical properties, right? So this is 3 square root 2, right, over 9 plus square root 6 over 4. Okay, and now between these two, what you're going to do is find the lowest common denominator, Well, between these two, let's say the lowest common denominator is 36. I'm going to multiply this by 4 and this by 4, this by 9 and this by 9. So now what I'm left with is 12 over square root of 2 plus 9 square root of 6 over 36. Okay, and this is as far as I can go. I can't really simplify this any further. And the fact is that I can basically try to reduce it, right, by dividing this, and this by 4. If I divide this by 4, right, so divide this by 4, you get 3. Divide this by, oh wait, not 4, sorry. Let's divide it by 3. Okay, let's divide this by 3, you get 4. Divide this by 3, you get 3, and divide this by 3, you get 12. So beyond that, your final answer, as far as you can go with this, is 4 square root 2 plus 3 square root 6 over 12. Okay, so this is the simplified form, and that's your final answer to this expression, right? So you can notice that this was it was pretty complicated as a question, but you can see if you do this step by step and you simplify this repeatedly, you can kind of solve for this very difficult trigonometric expression. All right, so that's the idea, really. Alright, so let's take a look at angles and standard position. And this is going to be a really useful model, especially when we look at future trigonometric equations, identities, as well as just in general the special angles when we look at the unit circle, right? So it is very advantageous to kind of understand angle and standard position. Now, before we can actually identify what that is, we need to understand that an angle is a degree of rotation. Angles are degrees of rotations between reference lines or rays. Okay, and a line we can understand is just is basically just like a straight edge, right? We're specifically looking at line segments, but a ray here is basically just like an arrow. Okay, and we're going to basically be looking at rays, and the two rays that we're going to be looking at is one of the rays is positioned on the x-axis. We're going to call this ray, we're going to call this ray the initial arm. So this is the initial arm. It's always positioned on the x-axis, right? So the initial arm is positioned at the positive x-axis. And another ray that we're going to be looking at is something called the terminal arm. And the terminal arm can be located on the initial arm or away from the initial arm. So let's say the terminal arm is located here. Okay, so this guy here is called the terminal arm. Okay, and the terminal arm is some rotation from the initial arm. Okay, and the degree of that rotation can be assessed by an angle theta. So this is theta. It's a degree of rotation between the terminal arm relative to the initial arm. So we're looking at rotations from the terminal arm relative to the initial arm, and we can understand that rotations can be positive or negative, right? So in standard form, positive rotations are counterclockwise, okay, and vice versa. So in standard position or standard form of an angle, positive rotations are counterclockwise, so that means that theta, if it's greater than 0 degrees, it's a counterclockwise rotation from the initial arm to the terminal arm, okay? And if theta is less than 0, this is a clockwise rotation from the initial arm to the terminal arm, right? So it's all the rotations are relative to the initial arm, right? And here we've shown that theta should be positive because of the fact that this is a counterclockwise rotation. You can see that it's basically going this way, right? The terminal arm was positioned here, for instance. Let's say it was located here, right? A negative rotation would be like that. So this would be negative theta, okay? That would be a clockwise rotation. Now, anyways, So we know that angles of standard form, there's an initial arm that's located on the positive x-axis. It's our reference point, and we are associating this with a terminal arm. The other thing to note about standard form is that the vertex of the two rays or the lines, vertex of the rays or lines should be the origin. Okay, so the origin being, so this is a vertex. A vertex is a combination. It's basically where two lines or rays meet. The vertex here is the origin, which is 0 and 0. Okay, and because the vertex is the origin, we can look at the position of the terminal arm from the vertex as a coordinate x and y. Okay, so we can look at the position of this terminal arm from the vertex, and this point can be expressed as x and y. Okay, so let's try to shorten this out. You can see that there's a grid system here. It's gonna shorten this terminal arm out. Say we place it here. Okay, using the grid system, this is a point, right? This is the point 2 and 3. Okay, so that means that the y-coordinate is 3, this coordinate is 2, and you can actually find the angle associated with that by using the trig ratio. And we can understand that x and y are 90 degrees apart, right? So in this case, if the point is 2 and 3, right, we can use the tan ratio, and then tan theta here is equal to 3 over 2, and then theta is equal to the tan inverse of 3 over 2. Okay, so you can actually figure out your trig ratios, right, because of the fact that x and y dimensions are 90 degrees apart. Furthermore, if you want to find the other ratios, you use Pythagorean theorem, and you do a squared plus b squared is 4 plus 9, which is square root of 13, right? Because if you do square root of 2 squared plus 3 squared, you get square root of 13. Okay, and you can also figure out your sine ratio. So sine, in this case, if this is theta, right, because it's a counterclockwise rotation, which is positive, right? Just gonna make this a lot nicer to look at. If this is theta, then we can understand that sine theta is 3 over square root 13, and cosine theta is 2 over square root 13. So that's another benefit of having the vertex at the origin, because we can represent the terminal arm as a coordinate, as a point of x and y, and then we can create a right angle triangle, right? So these are just some tenets that you kind of want to remember here, right? That counterclockwise, the initial arm is basically a reference ray, and its position at the positive x-axis. The terminal arm is a rotation away from the initial arm. Rotations can be, the rotations can be positive if they're counterclockwise, negative if they're clockwise, and the vertex's position at the origin and the terminal arm's position can be represented in terms of x and y. Okay, so this is an angle in standard form, so make sure you guys can kind of understand that. All right, so the next thing we're going to be looking at is what we call a unit circle. It's going to take in this idea to account, right? And you can also understand that if you do a full rotation of this terminal arm, right, you do a full rotation of this terminal arm from the initial arm, and you go back to its original position, you actually create a circle. Okay, and then the terminal arm, the length of the terminal arm here becomes the radius of the circle. Okay, so that's another idea that you can kind of understand. All right, so we'll move forward. Okay, so earlier we said that our special angles were angles where the trig functions would give us ratios that we would know the exact values of, right? So in the special angles we discussed were 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees, 270, and 360 degrees. Okay, so out of all of these, out of this entire set, we just looked at these three, 30, 45, and 60, and we identified them using the special triangles. Now, what I'm going to do now is I'm going to look at the rest of the special angles. I'm going to show you a way to find their values. And this method is going to be through the use of a unit circle, right? So I'm going to construct, in order to look at the unit circle, we need to look at angles in standard form, right? So I would advise you guys to kind of review that video regarding angles in standard form. Alright, so here's our Cartesian plane. I'm going to take a look at angles in standard form. So recall that if we're looking at angles in standard form, an angle is a degree of rotation from lines or rays, and one of the rays is a reference ray that we're going to be looking at, and it's called the initial arm. It's located on the positive x-axis, right? And the other ray here is basically going to be some angle at or away from the initial arm, and this is called terminal arm. And we also stated that the vertex was 0 and 0, and then positive rotations were counterclockwise rotations, right? Now, a unit circle is a special type of it's a special type or case of angles in standard position. We know that a full rotation here, if I did a full rotation, right? You know what? I'll use a different color so we don't have to. We know that a full rotation is going to give us 360 degrees, right? And full rotation is going to create a circle. Okay, so just don't mind my circle drawing abilities here, right? But assume that this is a circle, guys. Okay, so this is a circle. So full rotation of the initial arm, the terminal arm would give us a circle, right? We also stated earlier that we can look at the position of the terminal arm from the origin, from the vertex, which is 0 and 0, as a point x and y. Okay, so you can look at this position as x and y. Now, a unit circle is a special case where the terminal arm's length, which becomes radius if you have a full rotation, the radius of this circle here is going to be 1 unit. Okay? So the radius is going to become 1 unit, right? And a degree of rotation here, call this guy theta. The degree of rotation here is basically going to create a right angle triangle, right? Because this point can be expressed as x and y, this coordinate here, this dimension here is x, and this dimension here, this dimension here is y, and this dimension here is x. So therefore, the ratios of the angles are as follows. Sine theta here is going to call this guy r, right? Sine theta here is opposite over hypotenuse, so it's y over r, right? Cos theta is basically x over r, and tan theta is basically y over x, okay? Now there's a few things you want to kind of note here. We said that this unit circle has a radius of 1 unit, so r here is 1. So because r here is 1, then we basically, sine theta is equal to y. Because r here is 1, cos theta is equal to x. And just from this, you can note that tan theta is y over x. Because sine theta is y, it's basically sine theta, and cos theta is x. We get tan theta is equal to sine theta over cosine theta. This is actually a really important identity that you're going to be using a lot later on. And this is, this is the quotient identity. Okay, so this guy here is quotient identity, right? And basically tan of any angle theta is equal to sine of that angle divided by cos of that angle. Okay, so keep that in mind. So we understand that notion, but we also stated that points can be expressed as x and y, right? So using that notion, because sine theta is y and cosine theta is x, therefore points can also be expressed as cos theta and sine theta. So we can look at a position of the terminal arm by looking at the degree of rotation of its angle. Okay? Now, a few things to note here. Because we have a unit circle and the radius is 1, right? Then this point here, should be 1 and 0, because the radius from the origin, from the center of the circle to the outside of the circumference is 1 and 0. This point here should thereby be 0 and 1 if this is a perfect circle. This point here should be -1 and 0, and then this point here should be 0 and -1. So these are the 4 points that are associated with the circle, right? Now we can imagine that if the terminal arm was located at the initial arm as such, right, the angle here would be it would be 0, right? So theta here would be 0 degrees. And the point of the terminal arm would be in the form of cosine 0 and sine 0. Now this is also equivalent to the coordinate in terms of x and y as 1 and 0. You guys see that? So as a result, we can understand that cosine 0 is equivalent to 1 and sine 0 is equivalent to 0. So these are the values associated with cosine 0 and sine 0. Let's try another one. Right, so this is when theta is equal to 0 degrees. Let's see what happens when theta is equal to 90 degrees. So if theta was equal to 90 degrees, now the terminal arm would be located here. Remember that rotations are relative to the initial arm. If theta is 90 degrees, if it's positive 90 degrees, this is a counterclockwise rotation 90 degrees, right? So we'd expect the terminal arm to be positioned there, right? And if we look at that, then this would be relative to the angle cosine 90 degrees and sine 90 degrees. And this would also be related to its point in this x and y coordinate 0 and 1. So this tells us that therefore cosine 90 is equal to 0 and sine 90 is equivalent to 1. Okay, so those are the values for cosine 90 and sine 90. Okay, let's take a look at another example here. Okay, so let's say that theta is equal to 180 degrees. So if theta is equal to 180 degrees, our terminal arm this time would be rotated all the way here to counterclockwise rotation. It would end up there, right? And in this case, we would have the point would be cosine 180 sine 180, and it would be equivalent to -1 and 0. So therefore, right, let's use a different color so we don't get mixed up. Cosine 180 is equal to -1 and sine 180 is equal to 0. That makes sense? Right? So that's basically 1/2 of a quadrant. Let's take a look at the next special angle. So we figured out values of this, we figured out values of 90, 180, let's look at 270 and 360, right? Okay, so I'm just going to erase this guy, because we'll get back to that afterwards. But let's take a look at when theta is equal to 270 degrees. Okay, when theta is 270 degrees, our terminal arm can be located here. Okay, so if a terminal arm is located there, then the point equivalent here is cosine 270 degrees sine 270 degrees. And this is equivalent to the point 0 and -1. So therefore, cosine, you know what, let's use blue here. So therefore, cosine 270 degrees is equal to 0, and sine 270 degrees is equal to -1. Okay? And for the last case, when theta is equal to 360, you can actually notice that we just get back to, if we did do the rotation from the initial arm, we just get back to 0 degrees. So it's the exact same values as 0 degrees, right? So if theta was equal to 360, right, then you'd have point cosine 360 sine 360 is equivalent to 1 and 0, and you can see that cosine 360 is 1 and sine 360 is 0, right? So therefore, cosine 360 is equal to 1, sine 360 is equal to 0, and this is the same as cosine 0 and sine 0, okay? Those are the values of our respective special angles, 0, 90, 180, 270, and 360. Okay, so we've looked at values of angles that were acute angles, right? So acute angles being where theta was greater than 0, well, greater or equal to 0 degrees and less than 90 degrees. And we've looked at these acute angles and their particular trigonometric ratios. However, what if we have angles that are obtuse? So if angles are obtuse, they're greater than 90 degrees but less than 180 degrees. Okay, so what if we have obtuse angles? How do we determine the value of their trigonometric ratios, right? And the way we do this is we use something called a correlated angle. And the correlated angle, we're basically going to be looking at relating these angles to a related acute angle. How we're going to determine this is we need to go back and investigate our angle in standard form. So I'm going to draw out a Cartesian plane again. Okay, and recall that angles in standard form, we have an initial arm that's located on the positive x-axis. Okay, so this is our initial arm. And we looked at angles as degrees of rotations, specifically positive angles for counterclockwise degrees of rotation from the initial arm outwards. And we can represent the point of the terminal arm, x and y, so this was the terminal arm, to look at the position of the terminal arm from the initial arm. We can thereby figure out its angle, theta. Okay. Now we also looked at some of the primary trig ratios associated with this angle theta. We can understand that sine theta is basically the opposite side over the hypotenuse. Well, if we have a point x and y, this is the dimension x, this is the dimension y, sorry, and this is the dimension x. We know that the terminal arm will eventually become the radius of the circle if we have a full circle. Okay, so this is the radius. So the sine theta here, because x and y are 90 degrees to each other, sine theta is the opposite side over the hypotenuse being the radius, so we have y over r. You notice that these are both positive. Okay, so we're in the positive y. Radius is always going to be positive. Okay, so positive r. Cosine theta it's the positive x value over r, and tan theta is y over x. Okay, so these are the primary trig ratios in the first quadrant. So this is basically quadrant 1, right? And you can think about the reciprocal ratios as just the reciprocal of these. You just flip the numerator and denominator. Now, if we wanted to look at an angle in the second quadrant, and this is basically what an obtuse angle is, right? This is going to be found in the second quadrant, and the terminal arm would be found positioned, whoops, let's say that it's found positioned here, okay? I didn't draw this exactly the way, so let's say that we took the same terminal arm and we positioned it in the second quadrant. Let's say it's here, okay? Okay, so now we're going to have the point negative x and positive y. Okay, so this is negative x because this is in the negative, it's in the negative portion of the x coordinate, and we have positive y. And in this case, the angle would have a rotation that coincides with this value, theta. Okay, now this is an obtuse angle. However, we don't have particular ratio, that we don't have these well-known particular ratios for these obtuse angles. What we could do, however, is we can relate it to an acute angle, and this related acute angle, I'm going to call this beta, can be found here. Okay, so I'm going to use beta as my related acute angle, and we can use this related acute angle to make inferences about the obtuse angle. Okay, so theta. Now we can understand that if you do a full rotation from the initial arm all the way to this point here, this is a 180 degree mark. Okay, this is a 180 degree mark. So whatever our value of beta is, we can understand that theta is equal to 180 degrees minus beta. Okay, so keep this in mind. Let's take a look at the trig ratios for beta. Okay. So let's start with the sine ratio of beta. Okay, so the sine function of beta here is basically, and once again the radius is still out here, it's the length of the terminal arm. So the sine beta here is the opposite side over the hypotenuse. It's basically y over r. You can see that it's the same as sine theta, right? Cosine beta, however, is basically negative x over r. Okay, so we can notice that the sine ratio of beta is the same as sine theta, but the cosine ratio of cosine beta is equal to negative cosine theta. Okay, and the tan ratio of beta is equal to also negative tan theta. Okay, maybe just get rid of this. Negative tan theta. Okay, so what does this imply? Well, we know that theta is equal to 180 minus beta. So this infers that because sine beta is equal to sine theta, because they're both equal to positive y over r, this implies that instead of writing sine theta, I'm going to write 180 minus beta. Let's try to keep it consistent. Is equal to positive sine beta. Okay, so whatever our acute angle is, 180 minus that acute angle will give us the same value. Okay. We can notice here also that cosine 180 degrees minus beta, because it's cosine theta, right? I'm going to make the right side completely positive, is equal to negative cosine beta, right? So whatever the obtuse angle is going to be equal to negative value of the related acute angle, beta. Okay, and tan 180 degrees minus beta is equal to negative tan beta. Okay, so I'm going to make sure that the left side is completely positive. Okay, so these are my correlated angles equations, right, in quadrant 2. Now what's the relevance of this? Well, let's say that we had a value. Let's say we had to evaluate what sine 150 degrees was. Okay, and we can notice here that 150 is an obtuse angle. So this, we know that because it's obtuse, it's going to be found in quadrant 2. Well, we understand that theta here is 150 degrees. And we know that in the second quadrant, the correlated equation here, sine 180 degrees minus beta is equal to positive sine beta. Okay, so we understand this. And if we plug this in, we understand that theta here is equal to 180 minus beta. So in this case, theta here should be equal to 150. So all of this here should be equal to 150. And if theta here is 150, then 180 minus beta should be equal to 150. Beta should be equal to 30 degrees. If I rewrite this equation, sine 180 degrees minus beta here should be 30, should be equal to sine 30 degrees. So you guys can see that this is how the equation can be used and set up and for it to work, right? So you can actually notice that sine 30 is one of the special angles that we calculated, right? So sine 30 here should be equal to a half, and as a result, sine 150 degrees is equal to positive a half, and it's the same value as sine 30. That's how we can use related acute angles to figure out the values of obtuse angles, right? And if the obtuse angles have some relationship with the special angles, we can find their exact values. Okay, so in the next couple of videos, I'm going to show you guys the correlated angle equations for the third quadrant and the fourth quadrant. Okay, continuing on our discussion of correlated angles, right? Recall that we were looking at angles in standard position. Okay, and we looked at the second quadrant. Let's say that angles are now located, well, now the angles are greater than 180 degrees, but less than 360 degrees. And these types of angles are called reflex angles. Okay, so let's say that we're specifically looking at angles in the third quadrant, right? So the initial arm is always positioned on the positive x axis, and the terminal arm would be located somewhere away from that. So let's say that the terminal arm here is located, say, out here. Okay, and this is your terminal arm, and in this case this is a reflex angle, so the reflex angle itself would be right here, right? So this is the reflex angle of theta, right? You don't have to color this in, but this is the reflex angle of theta, and it's located out there. And we want to find the value of particular trig ratios of a reflex angle. So the way we do this is we need to find a related acute angle. Now the related acute angle has to be created with the x-axis in question. And it's basically, we're going to project this initial arm here. So this is your value of your related acute angle beta. So remember that beta here is your related acute angle. And if you wanted to look at identifying your angle, your reflex angle theta, in terms of beta, you can write theta as 180 degrees plus beta. Right? So if you add 180 degrees, so 180 degrees would basically mean all of this. If you add 180 degrees plus beta, then you basically will get theta. Right? So that's the idea, really. So theta is 180 degrees plus beta. And recall that in the first quadrant, right, if we had a terminal arm that was located in the first quadrant, such as here, I'm just using a different color so we don't get it confused, but say that our terminal arm was in the first quadrant, we stated that this point here is x and y. We stated that this was the radius, this is the x coordinate, this is the y coordinate, right? And the ratios as follows, if this is theta, right, sine theta was equal to y over r, cosine theta is equal to x over r, and tan theta was equal to y over x. And all these were positive, right? So let's take a look at beta here. Okay, so if theta was in the first quadrant, if it was an acute angle, these would be the ratios. Now let's compare this with related acute angle beta. So if we look at this point here, this is going to have a point negative x and negative y. So this is going to be negative x here, this is going to be negative y, and this would be r, right? And assuming that the length of r is the same in this case, I know it's not drawn to scale. If we took a look at that, we can know here that sine beta is equal, is equal to opposite side negative y over hypotenuse radius r, right? And this was actually equal, so sine beta in the third quadrant, you can actually see that the related acute angle is equal to negative sine theta. Okay. Now if we take a look at cosine beta in the third quadrant, we can see that it's equal to negative x over r, which is the negative value of cosine theta, so negative cosine theta. And tan beta, which is basically negative y over negative x, is equal to positive y over x, which is the same as tan theta. So just from this, in the third quadrant, our following equations will be as follows, right? So in the third quadrant, so this is your second quadrant, sorry guys. Right, in the second quadrant we said that only the sine ratio is positive. In the third quadrant we can see that sine theta, which theta is going to be 180 plus beta, sine theta, which is 180 degrees plus beta, is equal to negative sine beta. Okay, cosine 180 degrees plus beta is equal to negative cosine beta, and only tan was positive in the third quadrant, so 180 plus beta was equal to positive tan beta, right? So in the second quadrant we found that only sine was positive. In the third quadrant, we found that only tan is positive. In the first quadrant, all of our trigonometric ratios are positive. Okay? Now, how do I use this? How do I go about using these equations? Well, let's say that we had a related acute angle that was related to a reflex angle that was basically a special angle. Let's say that we wanted to evaluate for the value of, let's say we wanted to figure out what is cosine, let's do 240 degrees. Okay, what is the value of cosine 240 degrees? Well, what we have to do here is we know that 240 is between 180 and 270, and we can understand that the third quadrant is between 180 and 270 degrees, right? Excuse me. And then we can utilize this correlated angle. So we know that this correlated angle equation. So we know that cosine 180 degrees plus beta is equal to negative cosine beta. Beta is your related acute angle. Let's figure out what that related acute angle is. So we understand that this is theta. So theta here is 240 degrees. And theta is the same as 180 plus beta. So this should be equal to 240 degrees. So this tells us that 180 degrees plus beta is equal to 240 degrees. Beta therefore should be 60 degrees if you solve for this, right? So therefore cosine, right? Maybe use the different color here, but 180 degrees plus beta in this case is 60 is equal to negative cosine. Beta in this case should be 60. It's kind of like a function in a sense, right? In this case, we get cosine 240 degrees is equal to negative cosine 60 degrees, and we know that cosine 60 is 1/2, so cosine 240 is equal to negative 1/2. Okay, so that's actually the value of cosine 240. If you guys if you guys are skeptical, just punch it into your calculator and you'll actually get the same value of negative 0.5. Okay, so you can use these correlated angle equations to determine the exact value, or by exact value of the reflex angle counterparts if they are special angle equivalents. Okay, so in the next lesson I'm going to show you guys the correlated angle equations in the fourth quadrant, but what you want to understand from all of this is that in the third quadrant only the tan ratio. Alright, continuing on with our discussion of correlated angles, let's take a look at an angle value where theta is greater than 270 degrees and less than 360 degrees. So it's going to be in the fourth quadrant. And let's say that the terminal arm is located out here this time. Okay, so this is the terminal arm, right? And this has a radius of r if you do a full circle. And the point of this terminal arm will now be positive x and negative y, right? So in this case, the angle value would be a rotation. It's a reflex angle, right? So the rotation would be counterclockwise, and then it would extend all the way out here. The related acute angle is always based on the x-axis, so this is your related acute angle. Okay, so this is our angle theta. This is our related acute angle beta, and you can express your value of theta as some kind of expression of, or some kind of equation of beta. And you can write this as 360 degrees minus beta, right? So if you do 360, which is a full circle, minus beta, you'll actually get theta. Okay, so that makes sense. And now in this case, we can understand that if we looked at our first quadrant, right, so this was our first quadrant. One second. Okay, so this, if we looked at angles in our first quadrant, if theta was in our first quadrant, that this would have a point x and y. So this would be y, this would be x, this would be r, right? So therefore, sine theta was equal to y over r, cosine theta was equal to x over r, and tan theta was equal to y over x. And all of these ratios were positive. So we found that all of the ratios in the first quadrant were positive. Only the sine ratio was positive in the second quadrant. And in the third quadrant, we found that only the tan ratio is positive, right? So investigating the fourth quadrant, we're going to assess beta, our related acute angle. So beta was a related acute angle. Once again, just to reiterate, we are using a related acute angle to find values of our obtuse and reflex angles, right? So beta is a related acute angle, and if I looked at beta here, right, this would basically be x, positive x, this would be negative y, and if I looked at my ratios, sine of beta is equal to negative y over r, the hypotenuse, right, opposite over hypotenuse. Because it's negative, we can imagine here that this is going to be equal to negative sine theta. Okay, cosine beta is equal to positive x over r, which is equal to positive cosine theta. And tan beta is equal to negative y over x, which is equal to negative tan theta. So this also indicates that one of the ratios here are positive, and in this fact, the cosine ratio is positive in the fourth quadrant. Okay, so this is the fourth quadrant. Okay, so in the fourth quadrant, the cosine ratio is positive, right? And if we wanted to kind of simplify out these related angle equations, we can note that sine theta, instead of right there, we're going to write 360 minus beta. Sine 360 degrees minus beta is equal to negative sine beta. Cosine 360 minus beta is equal to positive cosine beta, and tan 360 degrees minus beta is equal to negative tan beta. Okay, so these are our related acute angles. These are our correlated angle equations in the fourth quadrant. Now, how we use this is, let's say that we want to evaluate cosine. Well, let's actually do a different one. Let's do tangent 330 degrees. Okay, so 330 degrees is between 270 and 360, so it's in the fourth quadrant. If we want to evaluate for tangent 330, then basically what we're going to be doing here is going to be utilizing this equation for tan, right? So we know that tan 360 degrees minus beta is equal to negative tan beta. In this case, our value of theta here is going to be equal to 330, right? So all of this here should be equal to 330. So we know that 360 degrees minus beta is equal to 330 degrees. So therefore, beta should be equal to 30 degrees. So if beta is equal to 30 degrees, and if we plug this into our equation, we can imagine here that tan 360 degrees minus beta, which is 30 degrees, is equal to negative tan 30 degrees. So wherever I see beta here, I plug in 30 degrees. Okay? And you can see here that tan 330 degrees is equal to negative tan 30 degrees. And tan 30 we know is square root 3 over 3. And because it's negative tan 30, it's negative square root 3 over 3. Okay, so that's how we can use our correlated angle equations to determine the values or the ratios of reflex angles. Alright, just to summarize for everything we just kind of discussed about a related acute angle, our correlated angle is determining the ratio of obtuse angles, reflex angles of the respective trigonometric functions. We found out that in the first quadrant, all the ratios were positive, and these would be acute angles between 0 degrees and 90 degrees, right? And we can understand here that all the ratios here would be acute angles, so they should all be positive. In the second quadrant, however, we found out that our terminal arm would be would create angles. Right, our terminal arm would create angles theta would be between 90 degrees and 180 degrees. Okay, so here theta was between 0 degrees and 90 degrees, and these would be obtuse angles. Okay, and we found out that only the sine ratio was positive, right? So one way you can kind of determine this is we'd use the modifier beta, which was located here. Okay, so beta would be located there, and if we wanted to represent our angle theta, the modifier here would be theta is equal to 180 degrees minus beta, right? And because we know that sine is only positive in the second quadrant, therefore for the second quadrant we write that sine 180 degrees minus beta is equal to positive sine beta. Cosine 180 degrees minus beta. So all you have to do really is to memorize the modifier, and you just have to memorize the sine, right? So this is a great way to just kind of summarize through that. I would just kind of sit down, memorize this, and try to do some questions. So you do 180 degrees minus beta is equal to negative 10 beta. Okay. In the third quadrant, the terminal arm existed somewhere here. Okay, so here's our terminal arm, and we can notice here that the angle in question extended all the way out here. So this would be a reflex angle. Remember that we're doing all of these rotations from the initial arm found on the positive x-axis. And in this case, in the third quadrant, theta is equal to 180 degrees plus beta. Okay? And we found out that only the tan ratio was positive in this quadrant. So in quadrants 3, tan 180 degrees plus beta is equal to positive tan beta. Right? Sine 180 degrees plus beta is equal to negative sine beta. So all you have to do is memorize the modifier, and cosine 180 degrees plus beta is equal to negative cosine beta. Okay, so that was in the third quadrant. And lastly, in the fourth quadrant, we found that only cosine was positive, and the terminal arm would exist out here, right? And this angle here would also be a reflex angle, and it would extend all the way like that. Maybe we should draw it out here, right? So it would extend all the way out here. Whoops. Okay, and it'd be a reflex angle, and our related acute angle in this case was here. Okay, I think I forgot to mention the related acute angle where you draw it. You always have to make sure you have a positive x-axis, okay? Sorry, you always have to have an x-axis. It doesn't have to be positive. So in this case, our modifier, in case of finding theta is equal to 360 degrees minus beta. So that's our modifier for quadrant 4, and we found that only cosine is positive. Because only cosine is positive, then sine 360 degrees minus beta is equal to negative sine beta. Cosine 360 degrees minus beta is equal to positive cosine beta, and tan 360 degrees minus beta is equal to negative tan beta. Okay, so those are our correlated angles, and it's good enough. It's good to kind of just memorize this cast rule, the Cartesian plane, where cosine is positive in the fourth quadrant. Everything, all the ratios are acute and positive in the first quadrant. Sine is positive in the second quadrant when we have an obtuse angle, and tan is positive in the third quadrant when we have a reflex angle. So I would memorize this. I would memorize the modifiers for each of these quadrants, and the next step here would be to do some questions.